Good afternoon, and thank you for being here today. Across our country and around the world, climate change and water scarcity are creating serious challenges. Water costs are rising, drought is more frequent, and people need smarter, sustainable solutions. That's where I, Joe Garcia, come in. I provide rainwater harvesting services powered by advanced water engineering technologies. These systems not only conserve water and lower costs, but they also mitigate flooding by capturing excess rain and preventing neighborhood inundation. In partnership with Water Engineering Technologies, I'm building a network of dealers, expanding operations, and creating new jobs. So, while we help you save money and secure water, we're also growing an economy, one dealership and one job at a time. Let me help you turn rainfall into long-term savings, flood prevention, job creation, and sustainability. One of the most interesting things about drought is that it doesn't just reveal a water shortage, it reveals history. In Texas, dinosaur footprints appeared on river bottoms after being hidden for millions of years. On the Mississippi River, long forgotten, the Diamond Lady, a floating casino emerged from the water. At Lake Mead, receding water levels exposed shorelines not seen in decades. The bottoms of our rivers and reservoirs are like history books. When the water disappears, the past begins to tell its story and our future. This drawing illustrates subsidence, a process in which the land's surface gradually sinks. Subsidence can occur when groundwater, oil, or natural gas is extracted from underground formations. As these resources are removed, the pressure that helps support the soil and rock layers decreases, causing the ground above to compact and settle downward. Simple explanation. Imagine a sponge filled with water. If you squeeze the water out, the sponge becomes thinner. The same thing can happen underground when too much groundwater is pumped out. The land above slowly sinks. Why it matters? Subsidence can increase flooding risks, damage roads, buildings, pipelines, and other infrastructure, and reduce the natural storage capacity of underground aquifers. Conserving water and using rainwater harvesting systems can help reduce the need for groundwater pumping and help slow subsidence in some areas. This scientist is demonstrating the sinking of the land, known as subsidence. Standing beside him is a research scale that was installed in 1915. The scale is over 12 feet tall today and continues to grow as the land sinks, at a rate that once reached as much as 4 inches per year. This was once one of the most luxurious neighborhoods in Baytown. As residents noticed their community slowly sinking, they tried everything they could to keep it above water. They built barriers, raised structures, and even used pumps to remove water. But after years of subsidence, the ground had dropped so much that when a hurricane arrived, there was simply no way for the water to drain away. What had once been a beautiful waterfront neighborhood became a powerful reminder of how groundwater, oil, and gas extraction can permanently change the landscape. These are a couple of pictures from my neighborhood, and I'm sure they look a lot like yours. Everywhere we look, we see more concrete, more buildings, more parking lots, and fewer places for rainwater to soak into the ground. Instead of replenishing the earth, the rain quickly becomes runoff, flowing into storm drains, rivers, and eventually the ocean. Water follows a natural cycle. It wasn't meant to rush off our neighborhoods as fast as possible. Some of it should return to the ground, where it can recharge the aquifers beneath our feet. Those aquifers are the source of much of our drinking water and help support our communities during times of drought. A few inches of land sinking each year may not seem like much, but over time those inches become feet. As subsidence continues, drainage patterns change, flooding becomes more common, and neighborhoods become more vulnerable during heavy rains and hurricanes. I believe we need to start putting water back where it belongs, into the earth, not simply into rivers and then the ocean. We can do that by capturing rainwater and using it in our yards, reducing our dependence on groundwater wells, city water, helping conserve our lakes and reservoirs. We should also build more rain gardens. That's right, rain gardens. They allow rainwater to soak naturally into the soil, filtering it and slowly returning it to the aquifer. If water stands in your yard for a day or two after a rain, don't always think of it as a problem. In many cases, that water is slowly soaking back into the ground where it can do the most good. Another important step is planting more native plants. Imported ornamental plants may be attractive, but native plants were designed by nature to thrive in our local climate and soils. Their root systems often grow deeper and stronger, helping rainwater penetrate the ground, reducing erosion, improving soil health, and supporting local wildlife. Nature has been managing water for thousands of years. By working with nature instead of against it, we can reduce flooding, slow subsidence, recharge our aquifers, conserve water, and leave a healthier environment for future generations. Here are some pictures I've taken over the years of rainwater catch systems or rainwater harvesting systems. This one was taken pretty close to 2020. 2020 BC, if you look at it closely at the bottom of the roof line, looks like they used bamboo with a hole in it to direct the water, and it would drain into a bowl of lava rock, very porous to filter the water, then underneath the bowl filter. The cistern looks like bull rocks, large bull rocks, and it has a drain at the bottom, maybe another piece of bamboo hollowed out and maybe capped off with something kind of stick. Well, okay, that's the I would have built rainwater harvesting system back then. Although the technology has improved, the principle is exactly the same today. Modern gutters, downspouts, filters, and storage tanks are simply updated versions of these ancient systems. For more than 4,000 years, people have understood that capturing rainwater reduces dependence on other water supplies, prepares communities for drought, and makes better use of the water nature provides. This sugar plantation near West Columbia, Texas, is a place I had the opportunity to visit after being invited to a meeting by the local Texas Soil and Water Conservation District. In those days, transportation to Houston was very different from what it is today. Before modern highways, much of the movement of people and goods relied on boats traveling through the bayous and waterways that connected communities across the region. Standing there today, it's hard to imagine the many chapters of history that unfolded on the property, from slavery to convict labor to its years under Governor Hogg, an important role the bayous played in connecting the plantation to the growing city of Houston. In the picture where the factory once stood are cast iron cooking tubs and a cistern. The next picture looks like it's more modern, as maybe within the 1900s when we start noticing that we had scarcity of water and subsidence. The picture of modern rainwater harvesting system, plastic tanks, PVC pipe, fittings, screens, filters, pump house, and a solar pump system. To be able to be on a complete, sustainable water system when needed. You will be able to use the first part of the water cycle before it runs through your yards, your neighborhoods, parking lots, storm drains, and other contaminated water path. This is the Houston City College located in Katy, Texas, where they give horticulture classes. The drawing of the greenhouse with the irrigation drip garden, tanks, and pump house. If you notice, there's a pencil pointing to estimate height of the tank on a raised foundation. That is to make a run from the downspout outlet to the first tank. HCC has asked a minimum of 4 feet clearance from the greenhouse to be able to do maintenance. The 4 feet is also plumbing code for any water structure. Here I am picking up rings for my foundation and water tank. The rings are not the easiest things to move. They're very awkward. Here I am now at HCC delivering the rings and the tanks. I'm laying out the rings 4 feet away from greenhouse foundation and approximately 1 foot clearance between the rings that I dug up the top portion of earth and filled it with crushed granite and tapped it down. This is the east side of the greenhouse prior to any installs. The manufacturer of the greenhouse was called to authorize drilling the vertical and or horizontal aluminum beam support. This picture is with components and pipe ran at 1/8 inch per foot drop to tank. This picture consists of a component known as the leaf eater, which is a wire mash cover to prevent leaves entering into the piping system. The second component, known as the first flush is calculated at 10% of 1 inch of rain per square feet of roof area. The third component is known as the 4-inch inline screen filter. This view is east side of greenhouse installed. The 4x4s were installed to hide the tanks and anchor them down to prevent from blowing away. Here you can see the overflow outlet at the top of the tank. You can see there is 7 feet PVC pipe with a 90 degrees elbow with another 3 feet PVC pipe to direct water away from the tank to dispersing into a bed of rock. Further, the outlet from the tank is better. There's approximately 2 foot by 2 foot by 6 inch cavity filled with rock at the outlet to cushion the impact of water to prevent erosion. There at the tank top overflow outlet at the elbow, there is a screen to help prevent anything from crawling inside of the tank and decomposing. The outlet at ground level has a hinge door with a screen on the door to prevent something from bedding in the pipe and the hinge to help with excess flow. The guard and edging is to retain the number 57 rocks approximately 1 inch. The plastic mesh on the edging was put in place to prevent water backing to the tank base. This is the north side of the greenhouse prior to pipe installation. There are a total of 2 gutter outlets on each corner of the greenhouse. This picture shows the further's gutter outlet with a leaf feeder and first flush. There should be a leaf eater at every downspout outlet. The first flush can be one large one calculate at 10% of roof area or various units at 10% per section of roof area. This picture, you can see what I did to run PVC pipe to avoid greenhouse component outlets and to miss the final gutter outlet. You can also see how I had to use elbows to miss the other gutter outlet. You can also see the final gutter outlet leaf eater and first flush unit. Last minute change, Houston City College decided to go with a solar energy pump. Well, at the time when they asked me, I was having backlash when I was in the Air Force. My first job was to go out and repair the Bombay doors on a B-52, so they gave me a little toolbox and a big black book and opened the door for me. So I put the solar system in. It's not bad. I started with the solar panel to make sure it was going to get plenty of sun and shade from the greenhouse was not going to cover it. I needed a pump house instead of a dog house for a pump. Needed to be bigger to store the batteries, the control box, and the pump. The first one I bought was from Amazon. It was a fragile little tin can with little screws. The HCC crew then told me they get hurricanes and twisters, so I had to mount it to the ground. I slow sloped the roof away from the tanks. In this picture, we have 2-inch PVC schedule 40 pipe valves to connect the tanks together. You can also see a turnbuckle with cable to hold the tank down at 4 locations per tank. The pipe is painted purple to identify it as non-potable water and to avoid cross-connection with potable water. This picture has a hose bib mounted on the shed connected to the solar pump and a gravity-fed valve 3/4 inch hose connector and a 2-inch connector for draining tanks or cleaning. There's an isolator 2-inch valve to disconnect gravity and solar pump. After all that painting, they asked me to cover with insulator. The final job of the installation is testing. Manuel says to bleed the pump system by disconnecting inlet water line, then bleed through a plug on the pump housing. Let air out until steady flow of water, and then hit the on switch. But with the gravity feed pressure, it was able to push it through the pump and out the hose bib, which I strongly recommend, less mess. The pump has approximately 23 GPMs at 45 PSI, which is plenty good. And the most joyful view of the whole job is the sunset with the greenhouse. Houston City College and the rainwater harvesting tanks made it all worthwhile. Thank you. From Water Engineering Technologies. Don't think it's over yet. We're not stopping at watering the roses and filling bird baths. That's just the opening act. Next, we're bringing rainwater indoors to flush toilets and wash clothes with pre-softened water. Then, with the right filtration and treatment, we're talking showers, brushing our teeth, cooking dinner, and even a cold glass of drinking water from the kitchen sink. And there's more. Every gallon of rainwater we capture is a gallon we don't have to pump from the ground, helping slow down subsidence. Every tank we fill helps reduce the rush of storm water that can contribute to neighborhood flooding. And when the next unexpected drought shows up, and in Texas, it always does, we'll be glad we saved some of that free water that fell from the sky. Rainwater harvesting isn't just about saving water. It's about building stronger, more resilient communities, one raindrop at a time.